All right, welcome back to Math 234. I'm still your host, Steve Dragoo, and today we're going to keep going with triple integrals because that's basically all we do for 2 weeks. Except this time we're moving to a new coordinate system. We're not super new because we have introduced it before, but this is the main unit we were building towards when we introduced that system. This is triple integrals in cylindrical coordinates. We'll start with just a brief view of what those cylindrical coordinates look like. They are basically polar coordinates, but with the addition of a z-axis, where z works just exactly the same as it does in rectangular coordinates. It goes straight up and down, which means most of the time, if we're looking to make a two-dimensional sketch, or if we're going to try to figure out what this thing looks like in 2D before going up to 3D, the plane we're going to want to draw is the ZR plane, where hopefully that angle theta doesn't play a role in what the shape looks like. As with these two objects, one looks like a cone, the other must be a parabolic, one of those things. An elliptical paraboloid. There we go. I just started the wrong way. So as long as our shape doesn't depend on theta, we can just go straight to the ZR half plane. We'll think of it as a half plane because we'll only look at going to the right on R, since wherever possible, we want to leave R as a positive number, and we'll only deal with negative R values if we absolutely have to. But as long as we get our choice for R, we'll claim that it's going to be positive. Same with theta, it gets its usual bounds of 0 to 2 pi because we'll just do one circle as long as we don't have to do more. Some shapes will require us to do that, but a lot of them don't. So whenever we get the choice, we'll keep theta between 0 and 2 pi and r being positive. If our shape did depend on theta, we could pick a specific half plane where theta is equal to some value and then sketch out what it would look like in that specific plane. But with these two guys, theta did not matter. Now, the next example relies on section 15.10, which we decided to move, which I still think is a good decision, because all we really need to know when we start talking about this thing that's the Jacobian is that we need to rewrite our dV differential, so the volume differential in cylindrical coordinates. And it looks very, very similar to polar coordinates when we did the same thing. We found that dA in polar coordinates was r dr d theta because that d theta needed to be multiplied by r in order to actually talk about how the point was changing. So if we come look at where that's coming from, I want to start by just looking at dV in our rectangular coordinate system. We have dz, dx, and dy, which each point parallel to their respective axes. And they talk about how a point out in space changes by just a little bit. And if we want to represent that same small change in a point, but in cylindrical coordinates, that's this next diagram, we'll need to use dz, dr, and r times d theta. The thing to be focusing on here is that d theta, right? If I just talk about a small change in the angle, that's really telling us how a small change in a unit circle would look, right? Unit circle being the little gray circle drawn in by the origin. But if I've got a point that's further out in space or somehow even closer to the origin than the unit circle, then d theta doesn't really describe how the point is changing, just describes how a small change on the unit circle, small little bit on the unit circle is changing. So if I want to talk about a change in the point, I need r times d theta. I need to multiply d theta out to my point, which means multiplying it by r, and then using that to describe how the point changes. So r d theta to describe a change in our point out in space. When we do eventually get to section 15.10, where we calculate a a Jacobian, we'll find that it was very motivated by this diagram, as well as the other one that we'll look at for spherical coordinates. So I suppose, yeah, prepare for that. So again, the real big idea here is that anytime I need to multiply in a dv, I'm going to get this r times dz dr d theta. So I have a little bit of my pirate accent poking through. Whoops. So one quick highlighted example, one that we did on Friday. We had this wedge that we're cutting out of a cylinder. But on Friday, we did it in rectangular coordinates. And this time, we're going to do it in cylindrical coordinates, which just means rewriting our bounds in terms of r and theta instead of x and y. So instead of one of our bounds being z equals negative y, that bound will be z equals negative r sine theta. Since we'll use r sine theta and r cosine theta for y and x respectively. And the real fun part is figuring out our bounds on theta. Because you can see in the integral, I've got it listed as pi to 2 pi, which is not exactly standard. But if I think about where all that's coming from, and notice I've kind of labeled in the sort of major angles that exist in our r theta plane. So the major angles for theta are drawn in green, starting from 0 on the positive x-axis, and then working counterclockwise from above to go around the whole plane. So the positive y-axis is at pi over 2, negative x-axis is at pi, negative y-axis at 3 pi over 2, before returning to the positive x-axis and coming to 2 pi. So 0 radians and 2 pi radians. Both are going to point in the same direction. And my wedge, or our wedge, the thing that we want to find the volume of together, exists entirely on the left half of the 3D space. And here, left half means I'm talking about the negative y direction. And so if we just think about our unit circle or this diagram, because both are going to tell us the same thing, if I want the negative y-axis part of the space, if I want all of the negative y values, I need the third and the fourth quadrants, which would be pi to 2 pi. Those would be the boundaries for our third and fourth quadrants. Which is why, again, we're integrating that thing from pi to 2 pi rather than 0 to 2 pi. I don't want the entire coordinate space. I only want the left half of it. And again, if we're going to integrate dv, because we're just after the volume, we need an r times the rest of our differentials. So just make sure that that r always gets multiplied in. But then we just integrate each of those pieces down the line in order. I ended up getting 2/3, which is the same result we got on Friday, but in our dz, dy, and dx integrations. Cool. All right. With that said, let's dive into a new example. So convert the following integral into cylindrical coordinates and evaluate that result. So let's start doing that. If I take a look at the thing that we've got here, we're doing dz, then dy, then dx. So if I look first at this point right here, that is going to be z equals y. All right, since I'm doing dz first, I'll have z equals y. But I'm going to come back to that one. No, I'm not. I'm going to come back to it, but I'm just going to leave it as is for now. Okay, so cross that bridge in a second. I did work inside out, but I really want to focus on switching to r and theta, which means the first thing I want to look at really is this equation. I think it's the most interesting one. I've got 1 minus x squared inside of a square root, and that is on the middle integral. So this guy should be of the form y equals the square root of 1 minus x squared. So I want to start by graphing that. So I think it'll be helpful to draw a sketch here. Otherwise, we probably won't really know what it is that we're after. So here is an xy plane. X goes here, y goes there. I'm after a circle with a radius of 1, right? Y equals 1 minus the square root of 1 minus x squared. That's a circle with a radius of 1, or rather a specific part of that circle, which I'll get to in just a second. Maybe make our circle slightly bigger. Good enough. So, in particular, if y is equal to the square root of 1 minus x squared, that is the top half of this circle. This guy right here would be y equals 1, the square root of 1 minus x squared. The gray circle that I drew in initially, that thing was x squared plus y squared equals 1, which means this bottom half is y equals negative the square root of 1 minus x squared. So just be careful when you're reading these triple integrals in rectangular coordinates and trying to convert them into polar or cylindrical, whichever one it might be, or effectively just going into polar coordinates right now. If we have just the positive square root of the equation of a circle, that'll just be a half of the circle. Because our lower bound is going to be y equals 0, which is this line right here. That guy's y equals 0. So already we're only looking at half of a circle instead of a full circle. But I can keep that going. I know that x, being our last integral to talk about, it's the third one, it's between 0 and 1. So one of those lines out here, this is x equals 1. The y-axis, that's going to be x equals 0, meaning the actual region I want to integrate over is just that spot right there. Just the first quadrant of this circle. Since it's got a radius of 1, that means it's the first quadrant of the unit circle in particular, in case anybody's keeping score. But all right, that's our integration region. So far, all we've really done is just graph the equations we were given from our rectangular coordinate system. And now we want to convert that into cylindrical coordinates. So if I'm thinking about the first quadrant on the unit circle, that's going to be between angles of 0 and pi over 2. All right, so if you haven't yet reviewed your unit circle this semester, I would recommend doing that once again, since it comes up kind of a lot. We do a fair amount with trigonometry. But at least some of the stuff probably is going to be difficult to forget. Right? 0 radians is the x-axis, pi over 2 radians the y-axis. So once we've got those two bits together, I think we're mostly ready to go set up this triple integral. So let's start trying to do that. Hopefully, I should have left myself enough space here. All right, yeah, good enough. So let's start with our integrand. We've got x squared plus y squared. That's just r squared. So I can substitute that in. Don't forget that anytime we do an integral in cylindrical coordinates or in polar coordinates, because they'll have the same Jacobian, you've got to multiply an r into your integrand. When I'm switching my dv or my dA over into polar coordinates, got to multiply by that r right there. Then the rest of it will just go in an order that seems to make sense. The original integral did dz first, so we'll do the same. And then let's go dr and d theta. At least try that. If we get halfway through and discover that that's not going to work, we can always come back and change the order. But starting with z, it hasn't really changed. We're still going to go from 0 to y. So keep in mind that y really needs to be r sine theta now, since that's our replacement for y. So we'll go there. Now, for our r limits, right? R is going to go from the origin out to that circle. So it's going to go from a value of 0, which is the origin, to 1. Because again, that's the unit circle. It's got a radius of 1. So R goes from 0 to 1, that being the origin, out to that orange half circle that's drawn in. And finally, we need our theta bounds. We know we're only doing the first quadrant, so that's 0 to pi over 2. And then we just have to integrate that thing. So 3 integrals in order. Ready, go. I'm still going to have 2 integrals left after I do the first one. All I have to integrate is dz. So there's not much to integrate there. dz integrates to z. I evaluate from 0 to r sine theta. So in the end, I will have 4 r's and 1 sine theta, all being multiplied together. R cubed times r sine theta. It's going to r to the 4th times sine theta. Still with a dr and a d theta, r from 0 to 1, and theta from 0 to pi over 2. All right, then let's go do r next, because it's the next one in order. So when I do my r integral, I get to treat theta as though it were a constant. So I just have to integrate r to the 4th dr, which is going to get me to 1/5 times sine theta. D theta, theta now finally from 0 to pi over 2. Right. R to the 4th should integrate to r to the 5th over 5, evaluated from 0 to 1, just 1/5. And then we do sine theta. Its integral. That'll be 1/5 times sine integrates to negative cosine. So cosine of pi over 2 is 0. Minus cosine of 0 is negative 1. And then that can all simplify to just 1/5. Zoom out for a second and take a look at all of those. So in the end, a value of 1/5. Another relatively quick way to integrate sine or cosine, if I'm doing definite integrals, the value or the area underneath sine or cosine in any specific quadrant. So if I'm just looking at sine or cosine, the area underneath its curve in any one quadrant, that area is always going to have an absolute value of 1. And it's either 1 or negative 1, depending on which quadrant you are in. So it can be helpful just to kind of know offhand that if I integrate sine or cosine over just the first quadrant, I always get a value of 1. But the reasoning for it is right there. Sort of the way that I would plug those in. If you prefer the definite, do the integral, plug in the numbers. A lot of trigonometry, though, is about taking shortcuts. So I'll just point those out as I see them. Sound good? All right. Then I'm going to move on to the next one. So we've got this solid region over here to the left. And what is it that I want to do? I want to find its volume. So if I want to find the volume of some shape, and we're going to do it the calculus way, that's going to mean taking the triple integral of dv. Actually, you know what? I do want to write it down here, I think. Volume. Stop that. Slide you a little bit over that way. Slide that in right here. So I need to just set up this here triple integral. So let's do that. It should have three integral signs. I'll just draw those in. And let's see, what equations do I have here? That red one on top, that looks like it's just 1 minus r. 1 minus r. The pink expression on the bottom looks to me like it is negative the square root of 1 minus r squared. Try again. 1 minus r squared. Because it's negative right there. dv, of course, has r times dz dr d theta. dz dr d theta. And I just need limits for my two remaining variables. Let me slide you a little bit over there. So if I take a look at both of these expressions, the spot where they intersect in the xy plane, that's going to create a circle with a radius of 1. So I'm going from 0 out to 1. So I'm starting from the origin and working my way out. And we're going all the way around the coordinate space. So theta is from 0 to 2 pi. I'm sure I've mentioned it before, but it's probably worth repeating. Your default assumption for theta limits should be just 0 to 2 pi. So start by thinking 0 to 2 pi, and if you can't think of any reason not to do that, leave it as is. Just go 0 to 2 pi. Reasons why we might not do that are we have maybe some sort of helix function, or maybe we're stuck to just a specific half of the coordinate plane, or possibly just a quadrant. As long as we're not doing something weird like that. 0 to 2 pi for theta. So now we get to integrate this thing. So let's do it. So if we integrate dz first, this is going to go to what looks like r minus r squared minus a negative r times the square root of 1 minus r squared dr d theta. Still from 0 to 1, and theta still from 0 to 2 pi. Now, that thing ought to get integrated. So let's give it a shot. If I'm going to do my dr integral, I'm just evaluating between 0 and 1. So that means it won't be too bad to plug all that stuff in. R is going to integrate to 1 over 2 minus r squared, r cubed over 3. Plug in 1 to get 1 over 3. And now to deal with the other half. So r times the square root of 1 minus r squared. I have a really nice u substitution that's going to work for me over here. U is going to be 1 minus r squared. So du negative 2r dr means that this next part integrates to negative 1/2. from my u substitution. Because I've only got r and I need negative 2r. So negative 1/2 from the u substitution. I am integrating a square root function. I'm integrating a 1/2 power. That's going to go to the 3/2 power divided by 3/2. I'll multiply by 2/3. And then I need to evaluate that thing at 1 and at 0. If r is 1, 1 times 1 is 1 minus 1 is 0. Excuse me. So 0 to the 3/2 minus, plug in 0 for r, 1 minus 0 is 1. And so I get 1 to the 3/2. And that's my r thing all the way integrated. I still have a d theta that I haven't dealt with yet. It goes from 0 to 2 pi. So even before looking at all of whatever else is going to happen on the inside of that integrand, there is no dependency on theta. In fact, there hasn't been the entire way through this integral problem, this triple integral, which means this thing is a separable function as far as theta is concerned, so I could have separated the theta integral out at any time during this integral process, because I'm just going to get a result of 2 pi when I integrate d theta. Again, since it was separable, I could have taken that step anywhere in it I would have liked to. So sometimes it's easier to just get that out of the way right at the beginning and then focus on the rest. But I decided to just take it in order this time. I think on the next example, though, I'll show off when I think that that thing is separable. But let's come back to the rest of the mess that we have to simplify. So 1/2 minus 1/3 minus the rest of that stuff all multiplied together. So working our way through the part on the right, 1/2 times 2/3 is 1/3. Then I've got a 0 minus 1, which is -1. -1 times -1/2, or try that again. -1 times -1/3, so that's what I was going to simplify to, becomes +1/3. So I'm looking at 1/2 minus 1/3 minus 1/3 plus 1/3 for that third part, which simplifies to just 1/2. 1/2 times 2 pi is pi. So that was taking this thing the triple integral way, because we're in the triple integral section, so it just seemed like the thing to do. There might have been an easier method, though. Because these were two simple shapes that we were smashing together up top. Right? I've got a cone and I've got a hemisphere. Meaning, if I really wanted the volume, I could have just added up a cone and a hemisphere. Hemisphere. I'm actually kind of running out of space, so let me try writing it in over there. The cone was the one on top, so I think it was red. The hemisphere on bottom was pink. But a cone has a volume of 1/3 times the base times the height. The base is pi times 1 squared, and the height is 1. So 1/3 pi. Plus a hemisphere is half of 4 pi over 3 times r cubed. R just being 1 again. So 1/3 pi plus 2/3 pi is pi. I switch that over to, no, doesn't matter. Back to gray. So we'll just use that volume as a way to check our answer on this one. So don't forget that if you have simple shapes that you know some stuff about, you can check their volume just by their geometric equations. Same formulas that we've had since like forever at this point. I don't really exactly remember how long ago you would have learned volume of a sphere, but I imagine it was before this class. But we can always use that to check our answer if we've got some simple shape, which I think we have here. Which is not a bad idea to do, since these problems can get kind of long and involve a whole bunch of numbers, and I mean, I could easily see getting a small mistake in a small numerical mistake somewhere, one of these problems. So it's not a bad idea to check your work where you can, as several of you already know from watching me do numbers up here. But I digress. Said to our new integral, we want to evaluate a triple integral. Again, we've got x squared plus y squared dv, and E is the region enclosed by the surfaces z equals 9 minus 9 times x squared plus y squared, and z equals x squared plus y squared minus 1. So let's go sketch what that looks like. I'm going to want a one of these and a one of these. We'll again draw out that ZR half plane that I mentioned. So this is going to be Z, and that's going to be R. And I want to talk about these two shapes. This guy and this guy. So I think that first surface, 9 minus 9 times x squared plus y squared, is just 9 minus 9r squared. So that's a parabola that opens down. So this z equals 9 minus 9r squared. And the other bit looks like r squared squared minus 1. So r to the fourth minus 1. It's got to start below the r axis, but then it'll shoot up pretty quickly. Something like that. Z equals r to the fourth minus 1. And I'm interested in probably their point of intersection. I think that'll be helpful to know. Because ultimately what I want to do is, think of this as a 3D shape, right? So this thing would just revolve around the z-axis. If we think back to our surfaces of revolution from Calc 2, it's effectively what we want to do here. Take this shape, spin it around the z-axis to create the solid that we want to be integrating over, which means I need a projection of this thing down into the xy plane. Figure out what that looks like. I think that projection will, hey, come back here. Probably look a little something like that purple line. But that means I've got to figure out what it's going to look like. So again, I want the intersection of those two, the intersection of those two curves. Really, they're the two surfaces, but I'm pretending that they're curves so that I can just look at them in a plane. Which means I ought to set them equal to each other. Let's start with r to the fourth power minus 1 is equal to the other one, 9 minus 9r squared. Right? They're both equal to z. So if I'm setting them equal to each other, that's what that equation ought to look like. And then I just have to solve this thing for r. So let's get to it. This looks like r to the fourth plus 9r squared minus 10 equals 0. Right, I'll just move all of my terms over to one side. And then I have what is effectively a quadratic equation. And that thing is hopefully factorable. Though if it weren't, I could always use the quadratic formula. But this one is factorable. I've got r squared plus 10 times r squared minus 1 equals 0. And from that, I really just get one viable solution. Namely, that's that r is equal to 1. I could also get r equals -1, but again, wherever possible, we'll choose our r values to be positive. That's going to help us out a lot. So we won't worry about the plus or -1, at least not yet. So we'll just claim r is 1, because from the other side, no real solution out of r squared plus 10 equals 0. Since r squared should not be equal to -10, as long as we're sticking with the real numbers, which is what we're going to do. We'll stick with just the reals. So if I've got r equals 1, what did I really find here? Well, I think that means that my region of integration, if I just look at the xy plane, I'll convert this thing back to x and y. The region of integration is this circle. Hey, now. So this is the circle, r equals 1. And if I look at theta, well, it's going to start at the positive x-axis and work its way around counterclockwise through each of the major, well, it's really through all of the angles between 0 and 2 pi, but just to write out a few of them, that here is what they are. Hey, don't be like, okay. Here we go. Extend that axis down a little bit. So all of that to say, I think that theta should still be 0 to 2 pi, and r should be 0 to 1. Right, we can imagine that purple line right there, if I'm looking in the RZ plane, that is my circle, but staring at it from the side. Right, so I'm looking at that purple line right there over here projected down into the XY plane. So rather than it being just the part that is in the XY plane, I want the projection of my surfaces down in the XY plane, which again is why I'm looking at their intersection. The last couple of examples we did, the intersection of our surfaces just happened to already be in the XY plane, which made our math a lot nicer. But when our intersection is not already in the XY plane, we instead want to look at its projection down, which means solving for the intersection. Intersection really just means set two things equal to each other. This is why we set our surfaces equal, to then get a better idea or a better picture of what we're integrating over. But once we get to here, then it's just a matter of doing the triple integral, which hopefully won't be too bad. This is the triple integral of, let's see, we were doing r squared dv. So this will be r squared times r dz dr d theta. And I'll look at bounds for each of these pieces. Z, we know, goes from top to bottom, or bottom to top, I suppose. The bottom surface was r squared minus 1. The top surface, 9 minus 9r squared. Right, I can look over at the diagram that I drew to know that those are the ones that should go top and bottom. But an easy way to look at a surface and know which one ought to be on top and which one ought to be on bottom is to look at the constant term. The constant term usually tells us which one's on top and on bottom, as long as I'm near the origin or if I'm near the z-axis. Because on the z-axis, the orange surface starts at 9, while the blue surface starts at -1. Then orange opens down, blue opens up, and they intersect somewhere in the middle. So again, the constant term is how I was able to quickly know which one should go on top and which one should go on bottom. And then I can just draw my sketch to confirm that. But we know our R bounds should be 0 to 1. So we found our intersection was at r equals 1, and we're going all the way around our circle, so 0 to 2 pi. And let's go integrate this thing. So if we do that, notice once again, the theta doesn't have any dependency anywhere in the problem. Our original integrand has no dependency on theta. Both of the limits for z and for r do not depend on theta. Right? Z depends on r, but then r just has some numerical values attached to it, which means that theta integral is separable. So if I just integrate d theta from 0 to 2 pi, I get 2 pi. And I'm just going to knock that one out right at the beginning. And then go focus on dz. If I've got dz, I get to 9 minus 9r squared minus r to the fourth minus 1, which is going to be 10 minus 9r squared minus r to the fourth. And multiply all of that by r cubed. So 10r cubed minus 9r to the fifth minus r to the seventh. There we go. I don't know why that took a minute, but it did. All right, r to the fourth times r cubed is r to the seventh. And this just gets evaluated from 0 to 1. So now I just have to do that. So this looks like 2 pi times, it must be 10 over 4 times 1 to the fourth minus 9 over 6 times 1 to the sixth minus 1 over 8 times 1 to the eighth. And when I plug in 0, I get 0 for all three terms, since I'm just integrating powers of r. And we could simplify those fractions, or we could not. So let's not. It'll come out to a number, I'm sure. But that's good enough for now. Not get too lost in what we're doing. So one of the points that I think is nice about cylindrical coordinates, and we'll see roughly the same thing when we do spherical coordinates, is the actual integration tends to be pretty easy as long as you're comfortable with trigonometry. So again, review the unit circle. If it's been a minute, maybe look at a few of those trig identities. They could be helpful from time to time. But we usually get rather nice looking integrals when it comes time to actually integrate stuff in these coordinate systems. The hard part is just trying to figure out what our region looks like. And that's if we have nice shapes for cylindrical coordinates. I think for our last example, and one that was even an old exam problem, back when we were really looking to find difficult exam problems, take this, what's very obviously something that should be integrated in rectangular coordinates, and try to do it in cylindrical coordinates. But notice we're not even going to ask you to integrate the thing, we just want it to get set up. So here's this triangular region, very polyhedral. I think maybe, no, it's polyhedral. It's not quite a tetrahedron, but I digress. Take this shape, given the equations over there, which look very nice in the rectangular system, and try to convert those bounds into cylindrical coordinates. Ready, go. All right, so let's see what we've got here. Some of these don't look so bad. In particular, if z is equal to 4 minus x, that's really just 4 minus r cosine theta. That's an easy substitution, which is nice because I think that's the most difficult looking surface over here. That's going to be that guy up on top. But since we're in cylindrical coordinates, we get to keep z as just z. So we don't need to do too much to transform that one. Really, it's going to end up being the other bounds that are fun. So if I start looking at the other four equations, trying to decide which of these I think are nice to convert into cylindrical coordinates, I think the nicest one is just y equals x. Because that's just the line theta equals pi over 4. Right? Rather nice looking line. Right? If y and x are equal to each other, I'm just looking for the point on the unit circle where y and x are equal to each other. That one happens at pi over 4. They're both root 2 over 2. So that must mean we're looking at this line right here. Let me try and line that up a little bit better. Cool. So that's our line. Y equals x. Theta equals pi over 4. Now I've got to go deal with the rest. All right. Well, if I'm thinking about how d theta should work, right? D theta works its way from the inside out. So if, or dr, I think I said d theta, but I really want a dr. All right, I'm going to look at r moving this way from the origin outward. So if I'm looking for the pair of bounds that I want to set for r, well, then I've got some inside function and some outside function. I want to think about the way that r works. It's going to go from inside to the outside. So when I'm setting up my limits, I'm going to need an equation for that blue line, and I'm going to need an equation for that orange line. Oop. And finally, I said, and finally, I want to be thinking about theta, and theta really needs to start from the positive x-axis and work its way counterclockwise, which means I'm going to be starting from pi over 4 and working my way around. So I'm going to need this intersection point, that purple guy right there, where the blue and the orange intersect. So let's get to it. Figuring out the blue line and the orange line. I can see from my graph that the blue line is x equals something, and the orange line is y equals something, or both of those are just constant values. So if I look back over here, this must be my blue line, that must be my orange line, just by looking at them in rectangular terms. So what do we have? We've got x, which is equal to r cosine theta, and that's equal to 3. Nope, try again. Square root 3. There we are. And then that means that r is equal to square root 3 over cosine theta, since I'm looking to have this be an r boundary. For my orange line, I've got y, which I know is r sine theta, and it's equal to 3, which means that r is equal to 3 divided by sine theta. So there's my two r limits. And finally, I need those two things set equal to each other. So 3 over cosine theta, or root 3 over cosine theta, equals 3 over sine theta, to figure out my intersection point, which again should be some angle for theta. So solving this thing, I'm gonna have, if I move all my numbers to one side, this looks like it'll be 3 over square root 3. Multiply the thetas all to one side. Sine theta over cosine theta. So sine theta over cosine theta is 3 over root 3, which means tangent theta is equal to square root 3. So I can simplify that right side. And if tan theta is root 3, then theta is pi over 3. Try that one more time. And just like that, I've got all of my limits. So if I put them all together, try again. Of whatever that inside was, we'll come back to that in a second. Theta was going to go from pi over 4 up to pi over 3. Those were the last ones we figured out. Putting my shape back on screen, I know blue should be the bottom for R, so that is root 3 over cosine theta, or maybe root 3 secant theta. 3 over sine theta for the top, or 3 cosecant theta, if you were feeling spicy. And finally, 0 to 4 minus R cosine theta for Z. And there we have it. That's the last one. How am I doing in time? Over again, as usual. Sorry. One of these days I might actually finish on time, but I mean, we've seen how it's been. Cool. Right. So that's it for me today. I will see you guys again on Wednesday. We're going to do spherical coordinates. It's going to be so much fun. Okay. Bye, 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 bye.